and we'll be ready to go. First thing I want to know is if you want to see the projector today. No. Okay. Is if you have any questions, okay, from anything we've covered up till now. All right. Now, here is a place where nomenclature almost gets in the way, okay? I'm trying to find out. I'll look at the table of content. It'll be a lot easier than thumbing through the book. Okay, we just finished Chapter 3, Modeling with First-Order Differential Equations. No, I'm sorry, Chapter 2, Modeling with First-Order Differential Equations. And at least somewhere back there we mentioned, I'm pretty sure, homogeneity. And at the time we said it's not the same thing as what it's meant before. Well, now we're in 4.1.3.2, which is homogeneous equations, and it takes on a slightly different meaning. If you have had linear algebra, which some of you are currently in and some are not, but with linear equation we talk about, and you did this anytime. If all your constants are zero, we call that system homogeneous system. That's not the same thing we're talking about here. It's the same word, but with a slightly different meaning. What homogeneous means is same. Homo, is things are the same. Homogeneous. Does anyone know what homogenized milk is? Anybody? Homogenized milk. If you look at most of your milk cartons or jugs and stuff, you'll see it's pasteurized and homogenized. What does that mean anyway? Pasteurized means it's been treated to knock out certain bacteria. Right? A lot of bacteria. Okay? In fact, probably most of the bacteria. Okay. But what does homogenized mean? What is it if it's non-homogenized milk? Well, I grew up on a farm. Okay? And when I was little, like before, I can't think what grade it would have been, maybe something like 5th grade, we had a milk cow. And every morning and every evening, my poor old mom was down out there milking the cow. Summer, fall, winter, spring, out there milking the cow early in the morning and late in the afternoon. You had to milk Roxy or she would get really irritable, okay? So she was always doing it. We tried, but I never could get the hang of it, but Mom was really good at it. Had a lot of cats in too. That was a different story, but it was related. But when we would drink that milk, we fussed and complained. Why? Can you think of some reason? Pour a glass of milk, and especially if it was chocolate milk, which we preferred to drink chocolate milk, what would rise to the top? Little bits of butter. Because whole milk, the butter kind of floats around in the milk. So what homogenized milk is, it's been beat to death. So all those butter nodules or whatever you would call them have been broken into such tiny little pieces you can't tell where they are. That's what homogenized means. All the butter has been evenly distributed and broken up into tiny little pieces so you can't see where the butter is and where the milk is. Because we'd say, oh, there's butter in this. And my mother tried to skim it off. She was too good of a mom, and try to get us to drink it. But, oh, there's more, and we were obnoxious. Okay. With homogenized milk, you never see the butter, even in whole milk. It has butter in it, but it's all been literally beat to death so that the butter nodule particles are so tiny you can't see them. Well, that's when all your equations were equal to 0. Those were homogeneous equations, homogeneous equations. Okay? In this section, 4.1.2, we're going to be talking about homogeneous equations, but of a different kind. Okay? Now, Chapter 2 dealt with linear differential equations, right? What made it linear? No, I'm sorry. First order differential equation. What made it a first order differential equation? First derivative was the maximum derivative you could have. And then you could have the function itself, y. You could have y primes, y, and functions of x's. Those were your three choices. You couldn't have anything more. Okay? Now we're in higher order differential equations. So in higher order differential equations, if you're talking about homogeneous equations, here's what they mean. A linear, that means you don't have any derivative multiplied by itself or multiplied by any other derivative or multiplied by the y function itself. That's what we mean linear. The maximum exponent for any of these, you might say the degree of your differential equation is all 1. Okay? So a linear nth order differential equation of this form, remember what we used to call coefficients are now coefficient functions, a sub n of x, okay? And that sub n just identifies that as the coefficient function that goes with the nth derivative term. So this would be d n y over dx to the n, right? Okay? Plus the next coefficient function, and the only reason the n minus 1 is down here, it identifies this as a coefficient function that goes with the n minus first derivative of y with respect to x to the n minus 1. Plus, and you can keep on going, a to the n minus 2 of x, d to the n minus 2 y, d x to the n minus 2, okay, plus dot, 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 plus, you keep on counting down until you get down to the a sub 2 of x, d2 y dx squared, plus a sub 1 of x, dy dx, plus a sub 0 of x, okay, times y, sorry, and that's equal to some g of x. I didn't plan very well, did I? Okay, I meant to scoot that over enough so I could get it all in the same line. Okay, now, I'm sorry. Back off. I skipped a line. This, rather than g of x here, that's equal to 0. So I take back what I was just saying, almost. Okay. Now that's called a homogeneous linear nth order differential equation. Okay? When it's equal to 0. This is going back to what we were saying earlier. If you had exactly the same thing, all this stuff was exactly the same thing, but that's equal to g of x, which when g of x is not identically equal to 0, then this is called a non-homogeneous. Okay? Differential equation. Nth order linear differential equation. Okay. So, just some examples. 2y double prime, that means d2y dx squared, plus 3y prime, that's dy dx, minus 5y is equal to 0. Would that be homogeneous or non-homogeneous? That's homogeneous. Okay? How about this one? X cubed, y triple prime. Yuck. I've lost it. There it is. Plus 6y prime plus 10y is equal to e to the x. What would you say about that one? Okay, this one's homogeneous. This is non-homogeneous. Okay. Goodness gracious. Okay. Now, this is, I was saying things backwards. 2.5 is what I was trying to find here. I knew it was going to refer to it, but I just couldn't find where it was that it referred to it. Okay. The one back in 2.5, that's the one I was trying to find. Okay. That's the one where the powers are the same. If you go to page 71, homogeneous equations. Now, of course, this is in first order differential equations. These are homogeneous equations if every variable in every term, whether they're first derivative terms, second derivative terms, whatever, if the variables are all at the same power. The examples they give here are, find one, they have all. Here's one. X squared plus y squared dx plus x squared minus xy dy. Every one of those terms, x squared, y squared, x squared, and xy, all those are second degree terms. All the terms are the same. Now, it doesn't really matter whether you've got equal 0 or not, okay? A lot of these are equal to 0, but that's not what makes it homogeneous. What makes these homogeneous, back in 2.5, are the fact that the powers of the x's are the same in every term, okay? And then we did Bernoulli's where they weren't, but you could make them homogeneous, okay? Just a little bit of a refresher there, okay? Now, over here in 4.1.2, when they're saying homogeneous, that's back to our linear algebra concept where everything's equal to 0. That's what we mean by homogeneous here, okay? Not that the A of x's are all the same degrees or powers of x's as you have in the back in 2.5. That's not what we're talking about here. We're talking about equal to 0. That kind of homogeneous. Okay. Now, we shall see that to solve non-homogeneous linear equation, we must first be able to solve the associated homogeneous equation. So that's going to become very important now. We first do the homogeneous, associated homogeneous, then we deal with the equal g of x. So we always do the equal 0 first. Even if the original problem wasn't that, we always do that first and then go back and deal with the g of x. That's basically what they're saying here. Okay. Now, to avoid needless repetition throughout the remainder of this text, we shall, as a matter of course, make the following important assumptions when stating definitions and theorems about linear equations. Okay? This is equations like these. Okay? On some common interval I, the coefficient functions a sub I of x, that's a of n, a sub n minus 1, a sub n minus 2, whatever, and g of x are always continuous. Don't have any discontinuous functions in there. Don't have any 1 over x's and your interval is going from minus 1 to plus 3. Yeah, it's not going to work because 1 over x's are continuous there. Okay? So all of your functions, the a of x and the g of x, are continuous on some interval I. Okay? And here's the other one. This always is the case. This a sub n of x, this leading coefficient function term, can never be 0. Why? Because if that were 0, this would be a degree, this would be a n minus 1 order differential equation, not an nth order. Okay? Because that first coefficient can't be 0. Okay. That done, let's look at what they're calling differential operators now. All this before we can ever get to doing what we want to do. Okay? Now, this takes a little bit of explanation, but it's really not as bad as you might think. So, I wanted to clear the screen, and I hit the other thing. So, let me do it. Okay. Now, in the last rendition that I was doing here, before the examples, I was doing this. d ny dx squared. Okay? Now already we know another way to write that. We could write that as y and put the n in parentheses. If it's just y to the n, that's raised to y raised to that power. If it's in parentheses, that means it's that derivative, the nth derivative of y. Okay? There's another operator that does the same thing. And let's start with the lowest one. dy dx, which we could write as y prime. We can also write this way, dy. Capital D, y, where capital D stands for d by dx, or whatever the independent variable is. This could be d by dt, d by du, d by ut, anything, whatever your independent variable is, that d by d of that variable, that is what capital D stands for. Okay? Why introduce another syntax here? There's sort of a reason. It's going to make some things shorter later. Okay? Now, it's called the differential operator because it transforms a differential function into another function. So, for instance, this one. d of, I've lost it now. I just saw it. There it is. d of cosine 4x. What would you say that was? Say again? It means d by dx of cosine 4x, and what would that be? Negative sine of 4x, and put a 4 in front. That's it exactly. It's the same thing as d by d. Okay, d by dx. Okay? Same thing. Okay? Now, how about this? d of 5x cubed minus 6x squared. Got it. Very good. That's what we mean by capital D. It's not quite as easy as writing a prime, but it allows us a little more flexibility. You'll see in just a minute. Okay? So higher order derivatives can be expressed in terms of d in a natural manner. Okay? And here's what we mean by that. D by dx of dy dx. Give me what you think might be that. What's d by dx? That's your capital D, right? So that would be d of, and what's d by dx? dy. Okay? Now, what would be sort of the logical extension of that? d2y. Exactly. Now, there's nothing really being squared there, is there? Okay? But, is there anything being squared here? Or here? No. It's just saying, why do I have an n there and a 2 there? That was bad. Okay? That should be an n. Okay? Yeah, there's nothing being raised to a power there, so neither is there here. That just means it's one operator operating on another operator, the same operator, yeah, as many times as you have a d there. Okay, now sure, that's the same as y double prime, right? Yeah, but y double prime starts running into a little bit of limitations here because we may sometimes go up to triple prime, but we never go up to four primes. After a while, you'd see so many primes there you couldn't count them. They're so close together and so small, it'd be easy to make a mistake. Okay? So in general, what would this be? dny over dxn. What would that be in our new operator notation? D to the nth of y. Exactly. You're doing the nth derivative of y. D by dx of d by dx of d by dx of d by dx. Do it n times of y. Okay. That's it exactly. Okay. Where y represents a sufficiently differentiable function. I mean, if y is only differentiable like this one right here 3 times, then it can only go up to 3, okay? You can't do the fourth one, you're going to get zeros from there on, okay? But this one, on the other hand, unlimited number, you could do that one because it just bounces back and forth between sines and cosines and pluses and minuses, so it repeats it. But then you have the chain rule stuff multiplying in, so yeah, it never is the same. Okay. Now, could you tell me what you would imagine that to mean? D plus 3. Now, of course, it wouldn't just be a d plus 3, it'd be d plus 3 of y. Translate that for me. What does d stand for? D by dx, we're assuming x is the independent variable, plus 3 of y. Now, that really doesn't make a lot of sense because 3 is a number and d by dx is an operator. Well, that d is an operator too. But what would you gather was being meant by this? dy dx plus 3y. If you guess that, you're absolutely right. This operator operating on that function plus 3 times that function. So you're sort of mixing operators and number, but yeah, it kind of makes sense. And that would be y prime plus 3y, which you see all the time, right? Lots of time. Quite a bit of time. Okay. let's extend that. All right, if I erase this because I'm running rapidly out of room. Okay, everybody got it? All right. What you reckon this would be? D2 plus 3D plus 4 minus 4. Okay. If that was operating on some function y or g or whatever it happens to be operating on, then that would be the second derivative of that function, like y double prime plus 3y prime minus 4y, right? Because each operator is operating on a y, and then 4 is just multiplied by a y. So that would be d2y dx squared, or whatever your independent variable is, plus 3 dy dx. dy dx, say again. What's that? Yeah. Yeah. You would always follow that by some variable that was your dependent variable, not independent, but dependent. Yeah, always is written in front of that. Could be G, it could be Z, it could be just about anything. So yeah, that's what that is. Do you think you can extend that anymore? What would this be? 5x cubed d, lost it, 3 minus 6x squared dx, d squared, no, d cubed, ooh, yeah, d squared, okay, plus 4xd plus 9, okay, that's just an expression. That's a pretty ugly x, okay. Now, that's an operator. It operates on some function, y, g, whatever function you have there. What that would be is 5x cubed times the third derivative of that function minus 6x squared times the second derivative of that function plus 4x times the first derivative of that function plus 9y or 9, whatever the function was. Okay, and then you set it equal to whatever you want it to be equal to. Okay, it's just a differential operator. Okay. In general, we define an nth order differential operator or polynomial operator to be, now this is called a linear operator, and here's what that definition. L is equal to a sub n of x, this looks familiar, doesn't it? D to the n, that's a lot easier writing d to the n over dxn, can't even say it easily, okay? Plus a to the n minus 1 of x times d to the n minus 1, sorry. Man, earlier today, my head was clogging up. Now my throat is getting sore. I don't know what this means. I hope it's not bad. Okay. Plus plus d, I'm sorry, a sub 1 of x d plus a sub 0 of x. Okay, that could be an operator. Okay, now it would operate, and it's a linear operator because say, of this operator has d to only 1 degree. And that means derivative power. You don't have d squared. You don't have this one times a d to the n minus 5. You don't have this one times a y. It only is this. So that's what makes it a linear operator. There's no exponents on the operators. What? There's a plus. I forgot to put in my a sub 1 of x. Just like a n minus 1 of x. A sub 1 of x, d plus a sub 0 of x. Okay. These are just our coefficient functions, whatever they are. They could be constants. They could be 0, except this one can be 0. Okay? Or they could be actual functions of x, not of y. The last one is multiplied just usually by y. All right. So that's what we call the nth order differential operator or polynomial operator. Okay? L. So we have a differential operator, and then we have an nth order differential operator, which we then call L, or polynomial operator. Okay. Now, there's two basic properties of differentiation. Okay? And here's what they are. D of C f of x sorry. Goodness gracious, I'm about to gag. Sorry. Okay. So, a differential operator on a constant multiple of a function. Okay? I hope you can guess what this is going to be. It's going to be the same as that constant times the differential operator operating on just the function. Sorry. Okay? Where C is any real any real constant. The other of these, D, and you've seen these hopefully several times. Don't know if you've ever noted they keep popping up here. If D is operating on f of x plus some g of x, then that's also the same as D operating on f of x plus D operating on g of x. Now, if you haven't noticed yet, just about any time we define something, we'll also give it these properties. These are called linear properties, okay? Because the sum of two functions is, how do we say it? Derivative of the sum is the sum of the derivatives. We've said that many times before. Derivative of a constant times a function is the constant times the derivative of the function. We've said this about derivatives, we've said it about limits, we've said it about just regular old mathematical addition. If we're doing anything with something, we can split it up by the operator. If you can, if that's a legal move with this operator, which it is for derivative operators, differential operators, then we call those operators linear operators. And that's why they introduced the symbol L, which kind of combines all the linear things. Okay? Now, okay, this is one really long and loaded sentence. It starts as a consequence, and ends 5, 6, 7, 8 lines further with linear operator. And it's a messy sentence, but it's saying something pretty simple, okay? So here's kind of the summary. I guess that's the best way to express this as a summarizing statement, okay? L, this linear operator, acting on, oh, this is bizarre, we're having to start with braces, and alpha times f of x okay, I've lost, there it is, okay, plus beta times g of x is equal to, I've got to close off my quotes here. Now, I don't know why they went to a brace here, because they could have used a bracket. I would like a bracket better. I think a bracket is in between a brace and parentheses, but they used a brace. It's perfectly fine. This is equal to alpha times the linear operator on f of x plus beta times the g of x. I don't know where my lines are going. I guess you don't need, right, left off the L, okay. Okay. Beta L times g of x, okay. Now, nothing too new here. Is taking this linear operator that was made up of differential operators, remember, combined together, and you're operating with that on some constant times L plus a different constant times a different function G, and that would be pull this alpha out times linear operator operating on alpha alone, and that does require another parentheses. I thought it did. Okay. Plus beta times the linear operator operating on g of x, okay? So notice what you got going here. The linear operator worms its way into the parentheses, but the constants worm their way out of the parentheses, okay? Both of these can go on at the same time, that's fine. But the linear operator stops at the function, and the constants stop when they're outside everything else, outside the function and outside the linear operators and everything else. That's probably a weird way to express it, but it does seem to fit what's going on. Okay. Now, let's look at differential equations. Any linear differential equation can be expressed in terms of the denotation so you have something of the order of y double prime, this is going back to how we used to write it, y double prime plus 5y prime plus 6y is equal to 5x minus 3. Sorry. My head is really giving me fits. Okay. All right. Write that in differential operator notation. In other words, using D. Say again? D2 plus 5D, no 6, operating all on Y is equal to 5x minus 3. Okay? Yeah. Okay? Now, if you define this operation as your L, then you could write this as L of Y is equal to okay. I don't see where they're getting their 0 in the first one. I'm trying to see that. Oh. Write them in the, okay, right back at the very beginning when we wrote the homogeneous form and then the non-homogeneous form. This is the homogeneous form of that thing, and the second would be the non-homogeneous. Now, are they going to like for you to do that too frequently? Probably not. They will, well, they just call this G of X. Okay. The thing I don't like about it in the same problem, this is looking at the homogeneous case, that's looking at the non-homogeneous case. The same operator is operating on both of them. So that's legitimate. Just realize one on the left is homogeneous, one on the right is not. Okay. Now, theorem 4.1.2 deals with what they call the superposition principle. Okay. So let's clear the screen and write it. I'm so sorry. I don't know where my head and throat and voice and everything else is heading here. Theorem 4.1.2, superposition principle for homogeneous equations. If we have a bunch of solutions, y1, y2, and on up to yk, okay, y sub k, and these are all solutions of the homogeneous nth order differential equation. Homogeneous linear nth order differential equation. Okay. And that would be that first one we did at the beginning of this subsection, the one they numbered 6, on some interval I. Okay. Then the linear combination, which is y is equal to, and this is generic solution y, would be equal to some c1 y1 of x plus c2 y2 of x plus c3 y3 of x, and all the way up. Okay, I said C3 and wrote 3C. I don't know exactly what's going on there. Plus dot 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 plus, and you finally get up to C sub k y k, because you have k of these equations. Okay, where your ci's, c sub I and I goes from 1 to k, just like we've had it before, are arbitrary constants. Okay? C sub I, where I is going 1, let's see. Okay. That this thing is also a solution. Now, things to note here. You're starting with a homogeneous equation, linear equation, okay? In order linear differential equation on some interval I, okay? So this can't be nonlinear, so that, you know, your differential equation that we haven't even written it down here, so that was in equation 6. You can't have, you know, say the third derivative multiplied by the second or the first of the equation itself. You can't have a y times a y prime. The y's and all the derivatives only occur once in each term, at one level in each term, okay, up to the nth order. That's what the linear means. Homogeneous, they're equal to 0. So these are your solutions. You know you have at least k of those linear solutions, or solutions of that linear differential equation on this interval I that you've got about. If you know that all these are, then you can also superposition them, write them as linear combinations of each other for any values for C that makes these work. You know, these are arbitrary constants C. They also form a solution. Okay, so 7 times this one plus 4 times this one minus 3 times this one plus the other. All these, they also solve that equation. Where these are arbitrary constants. Okay. Now this is for the homogeneous equation. Remember, that's part of it, as we're talking about now. Okay. Now, they do a little proof here of that theorem, okay? And they do it using their L operator, you know, that linear differential operator, okay? And you can play around with that and see, but it does come about. Now, there's 2 corollaries to that theorem, okay? Here's the first of these, and since this corollary is of the theorem, I'll leave it on here. A constant multiple, okay, y is equal to C1 y1 of x is a solution y1 of x of a homogeneous linear differential equation is also a solution. Homogeneous linear differential equation. Okay, so in other words, a constant multiple of any other solution, any one of those or any of them, is a solution. So not only is the whole thing a solution, but just pick one of them, any one of them, multiply it by a constant, it's going to be a solution as well. If y sub 7 is a solution, then 14y sub 7, or square root of 3 times y sub 7 is going to be a solution. Okay, that's the first corollary. The second corollary is that a homogeneous linear differential equation always possesses the trivial solution y is equal to 0. Homogeneous linear differential equation got all the things in the differential equation is always possesses the trivial solutions. I can't write. Okay, in other words, y is equal to 0. Okay, so remember homogeneous, linear, and differential equation, all that thing. That means that differential equation, however many terms it has and everything else, is equal to 0. All those things are operating on a y or a y prime or a y double prime or a y triple prime or y to the nth prime, whatever. Okay? If you set y is equal to, if that's all equal to 0, if y is equal to 0, so any constant you multiply that is going to be 0. And the first derivative of 0 is 0, and the second derivative of 0 is 0, the third derivative is 0. All those derivatives are 0, then the trivial solution is always going to be one of your solutions. That's going to be one of these y's up here. Maybe you call that the y sub 0. I mean, you don't have to, but it's always going to be a solution. That wouldn't be the case for the non-homogeneous. In fact, it couldn't, but it would for the homogeneous. All right. Let's see if we can do example 4. Here's a function. I'm going to call it y1. Don't call it x squared. Okay, y1 is x squared. And y2 is going to be x squared log of x. X squared times the natural log of x. Those two functions are both solutions for this horizontal homogeneous linear differential equation x cubed y triple prime minus 2xy prime plus 4y equal to 0. Now, it says those are true. Now, this is largely what the first test was doing. It's saying, verify that it's true. Now, I don't think we always need to do this, but not a bad idea too. So let's verify it. In order to verify it, what would be the first thing we're going to have to do? Take a derivative. Sounds good. So y1 prime would be 2x. y1 double prime, that's just 2 primes, would be 2. And y1 triple prime is going to be 0. Okay? Let's do the same thing for y2. y2 prime would be what? A little messier, but may surprise you. What would it be? Sorry? Okay. 2x log x plus x squared is the derivative of log x. 1 over x. Okay. Well, guess what that is? X squared over x is x. Okay. The exponent is 1. Okay. So, now let's do y2 double prime. Two log x. Okay. Two what? 2x over x. That'll just be plus 2 plus 1. Okay, I can simplify that a little bit. 2 log x plus 3. Right? How about y2 triple prime? 2 over x. Is that what you said? That's it. All right. Now, what we've got to show is, knowing that, is this differential equation true? Well, that first one, with y triple prime being 0, that's 0. I'm not worried about that one too much. So I have a minus 2x times y prime, which is positive 2x, plus 4 times x squared, because that was what y1 was, okay, is that equal to 0? What's minus 2x times 2x? Second, negative 4x squared plus 4x squared. Sure enough, that's equal to 0. All right, that one worked all right. Let's see if that next one did. Goodness, that one was weird. Okay, your y triple prime, this will be x cubed over 2x cubed over x. That's going to be 2x squared, right? Minus 2x times y prime, which is 2x log x plus x. Okay. Yeah, I've got to catch. Yeah, there's the plus 1. Yeah. What's that? Plus 3. You're right. I got lost. Wait. I got worried about that. I had not done something right. This would be 2. That's x cubed. Yeah. 2. Okay. So that's 2x squared minus 2x. No. See, here's your y prime. Yeah. So that's an x. Yeah. Okay. Plus 4 times your y, and this y would be 2, no, x squared. I'm sorry. I'm getting lost here. X squared log x. Okay. Let's see what this turns into. This is 2x squared minus 4x squared log x minus 2x squared plus 4x squared log x. And sure enough, this and this and this and that they add to 0. Both of them do solve that equation. Okay? We've shown it. They both are solutions for that differential equation. Okay? Now, what the next thing it says, it also gives an interval, 0 to infinity. This is an interval for x. Is that necessary? It's not necessary for the first one. Nothing wrong with that. It is absolutely necessary for the second. Because you see, you have a log x in there. X can never, you can't take the log of 0. You can't take the log of anything positive side of 0, never on the negative side, but on the positive side. So yeah, that works okay here, and especially since your derivatives you're going to be dividing by it. You can't ever divide by 0, but everything else you can. So that's why that limitation is there. These two solutions both are good in that range, and now it's saying their linear combination is. By the superposition principle, then y is equal to c1 x squared, I'm sorry, I can't read, which is c1 times y1 plus c2 x squared log x. They claim this is also a solution. Okay. If you wanted to go back and check it or test that, you'll see that when you take the derivative of this, first, second, and third derivative, you're going to wind up with exactly what we've got there, only with the C1 multiplied by 2x, 2C1x, and a 0. We're not using the y double primes any except to get to your y thing, but they all work the same way. Okay? And your second one, you would have, when you take the derivative of this, those derivatives would be just like that, only it would be 2c2x log x plus c2x, and the y triple prime would just have a 2c2 over x. Okay, you can trace that through, and you'll see that always keeps popping up there. It's the same in both, and then all those come to 0. They didn't ask us to, and I'm not about to volunteer to. Okay, verify that. So let's now look at the next one. Now I'm going to erase this. I don't think I need this because this is a new function of everything. All right. Here's a function, y is equal to e, goodness gracious, what is wrong? I say e and write 7 because that was the next thing I was going to say. My mouth's getting ahead of my pen, or my pen's getting ahead of my mouth or something. Okay. E to the 7x. They claim this is a solution to this thing, y double prime minus 9y prime plus 14y is equal to 0. Homogeneous equation. It is also a linear differential equation. It's also a homogeneous linear differential equation. And let's see, any other things it's got to be? Linear and homogeneous, that's it. then any constant multiple of that, we'll call it y. Okay. Now, we haven't really verified it yet. You want to do that quickly? It's not that hard to do. Well, how would you verify it? Y prime is equal to e to the 7x. Y double prime is equal to 49 e to the 7x. So y double prime would be 49 e to the 7x minus 63. Huh? 9 times 7. 63. Okay? 63 e to the 7x plus 14 e to the 7x. Okay? So basically it looks like that we need to add the 49 to 14. That gives us 63 minus 63 is 0. All right. So that indeed did work. Okay? It does satisfy that equation. So therefore, since this one did, y is equal to c e to the 7x also does. Okay? Because it's a linear, ordinary, second degree, homogeneous differential equation. Any multiple of that would be a solution as well. Okay, for various values of c, we see that y is equal to they just chose a few. 9 e to the 7x will work. Y is equal to 0. Y is equal to negative root 5 e to the 7x. All are solutions. Any c that you put in there. All right. Now, next thing that we'll do with this is talk about linear dependence and linear independence. These next two concepts are basic to study of linear differential equations, which is what we're studying, and these are important in lots of areas, but we're going to focus on them here. A set of functions, f1 of x, f2 of x, f sub n of x, okay, is said to be linearly dependent. For some reason, the pen's not right. Linearly dependent on an interval I if there exist constants C1, C2, C3, up to C sub n, not all 0, such that C1 F1 of x plus C2 F2 of x plus C3 F3 of x plus plus Cn Fn of x, all right, is equal to 0. Okay, now what do we mean by this? Linearly dependent if you can find some set of coefficients, not all zeros. Certainly if you pick all these zeros, then yeah, that's going to guarantee to be 0. But you got to have at least one of these that's not 0. okay? And yet the sum of these times the function, the linear combinations of them, the function, is equal to 0, then we say that this set of functions is linearly dependent. Well, what does that mean? Well, let's just say there was only one C that was not 0, okay? Let's say it's this one, okay? This C3 is not 0. Say it's something else, okay? 17, okay? But the sum of all these others are 0, okay? But then 17 times F3 is 0. That means F3 would have to be 0, right? Okay? But also what you could say is this one would be, subtract this from both sides, and then all these others would be 0, right? Well, that means this function here could be written as some combination of all those others. So one depends on all the others, okay? That's linear dependence, okay? If a set of functions is not linearly dependent on the interval, it's said to be linearly independent. So that means you can't come up with a set of C's that are not all 0 to give you that. And if you cannot, then that's linearly independent. Basically, that's what it's saying. Now, again, it's a concept you run into repeatedly in math. You know, you may not have hit it much now, but I think if we haven't hit it yet in linear algebra, we're going to hit it big time there, okay, because it's a basic concept of it. So in other words, a set of functions is linearly independent if on the interval I, if the only constants that we can have that makes this true is if every one of those constants is 0. You can't have a set that's not, because if they weren't, then you could take all that were equal to 0, move the others to the other side, and then you have those, depend on each other. For all the C's to be 0, then that would be linearly independent. Okay. I think we're out of time. Okay. We almost got to where I left off one other time. So I'm just going to back up one top of a paragraph, and let's see. We didn't quite finish, well, this is one long section, 4.1 point, whatever it is, 3. Wow. No, 2. Then we'll do homogeneous later. So you can do any of the, either 1 or 3 or both. Any of the odds, either 5 or 7 or both. Do number 9, do number 11, and do number 13. Then for the homogeneous part, do any of the odds 15 through 21. And we'll stop there because we haven't done what they call the fundamental set. That's what we'll do next time. Okay. All right. And I can't remember if I told this class, and since I've still got this on here, y'all don't matter much because I think all of you have done it. But they did ask for last week, finally, for us to do the midterm progress report. So if anyone hadn't turned in anything yet, and I think there's only one person in this class who hadn't, and that's the person who's not been here yet. I hope I'm saying that right. Then I had to turn in something on you. But I think all had turned in something except one. And it's the person who's trying to do it remotely. All right, that'll do it for